Non-singular matrices. We've seen this adjective before. Let's see why it's so important. So let's go back to the theory of systems of equations for a moment. So on the left here, I've written down a system with 3 equations in 3 variables. And remember, we can always represent any system as a single matrix equation. AX equals B, where A is the coefficient matrix of the system, X is our vector of variables, so that's the unknown we would eventually like to solve for, and B is the vector organizing the constant scalars to the right of the equal signs. So the idea here says, well, if to solve a system of equations, I just want to find the vector X, why couldn't I just do what I normally do in ordinary arithmetic and take the equation AX equals B and just solve for X? Now, if we were working with ordinary scalars, and this were a scalar equation, how would we solve for X? We would divide by A. And this would give us the expression X equals B over A. So this seems like a reasonable question. Why not just divide by A to get the answer to our problem? But the issue here is, I know how to multiply matrices, but I don't have any theory for dividing matrices. And this will be the first thing I'd like to address when it comes to non-singular matrices. And this will lead us eventually to this notion of matrix inverses. Okay, so when it comes to matrix inverses, there's some language that we need to get right up front here. So let's say that I'm working with an M by N matrix called A. Well, it might be the case that this matrix A has left inverses. When we say left inverse, what we mean is any matrix I could multiply A on the left by to produce the N by N identity matrix. It's also possible that this matrix has right inverses. This would be any matrix we could multiply A on the right by to produce the M by M identity matrix. So any matrix might have left inverses and also might have right inverses. Now, if A happens to have both, so if there's a left inverse L and there's a right inverse R, something interesting happens. The matrix L, of course, is the same thing as L times the M by M identity matrix. And of course, if R is a right inverse, that means A times R is the M by M identity matrix, so I can make that substitution. And I can regroup my parentheses here, and this would give me the expression L times A times R. But if L is a left inverse, that means L times A is the N by N identity matrix. And so now I would be looking at the identity matrix times R, but that's just equal to R. So this is a sequence of equalities that says if we have both a left inverse and a right inverse, then L equals R. And this is guaranteed. So a matrix may have left inverses, it may have right inverses, but if it has both, then this calculation says then there's only one. And in this case, we would say that A has exactly one two-sided inverse. So it's the only matrix that would work on both sides to multiply to give the identity matrix. And we would, in this case, denote it by A to the negative 1. Okay, so the idea is that we say that a matrix A is invertible if such an inverse exists. And so how can I verify if a matrix is invertible? Well, if I'm lucky enough to have a candidate for the inverse, I can check if that candidate is indeed the inverse. So for example, I have 2 equations here, and in both of these equations, I've taken the same A, and on the left, I've multiplied by this 3 by 3 matrix. And on the left-hand side, what I'm finding is that if I take A and multiply on the left by this matrix, I produce the 3 by 3 identity matrix. Now, if I take the same A and multiply by the same matrix, but this time on the right, this will also produce the 3 by 3 identity matrix. So someone has given me this matrix A, and they have given me this other matrix, and we together have verified that multiplication on either side of A for this particular matrix produces the identity matrix. So in this situation, we would say that A inverse exists, and it equals this matrix we've been multiplying by. And consequently, because A inverse exists, we say that A is an invertible matrix. Now, there's a huge word of warning here. Many matrices are not invertible. What that means is that no matter what you multiply some matrices by, you'll never produce the identity matrix. Here's an example to illustrate the point. So here is a perfectly good 3x3 matrix called A. And if you multiply by any 3x3 matrix, so I'm leaving everything here as variables, you'll produce something. But the thing is that because this matrix A is structured in the way it is, whatever you multiply by on the right will produce a row of zeros at the bottom. And in particular, in the 3-3 position, you'll never equal 1. This means that no matter what I multiply A by, I will never get the identity matrix. So this matrix A is not invertible. And no matter what I multiply A by, it'll never be the inverse of A. So this is a word of warning. When we're talking about inverses, this is the kind of thing that only applies to some matrices, not all matrices. Okay, now what good is a matrix inverse? Well, a matrix inverse is extremely useful for solving systems of equations. So let's say that I'm working with a matrix A, and that I'm lucky enough to have its inverse. So in this setup here, I have a matrix A, and I have its inverse. And let's say that someone gives me some vector B. In this case, I'm studying the vector B, whose coordinates are 2, 0, 2. Well, let's say that I was studying the system AX equals B. That's not new to this lecture. We learned how to solve systems through the Gauss-Jordan elimination procedure. What I could do is I could take my coefficient matrix A here, and I can augment with the vector B and do my row reductions, which are supplied to me by the Gauss-Jordan algorithm. So that's one way to solve the system. But the problem with this approach is that it's time consuming. It takes a lot of effort to do all of those row reductions in the Gauss-Jordan algorithm. And why would I go to all that trouble if someone just gives me the matrix inverse? If someone gives me the matrix inverse, then I know that AX equals B is the same thing as what I would get if I multiplied on the left by A inverse. And so that would give me A inverse times A times X times equals A inverse times B. And since A inverse times A is the identity matrix, this would simplify to X equals A inverse times B. So I know immediately that in this situation, if I'm studying the system AX equals B, the unknown X I'm looking for is the same thing as A inverse multiplied by B. So I did that matrix multiplication, I took A inverse, and I multiplied by B, and this produced the X I was looking for. The coordinates here are 10, 2, 4. Now this just so happens that that's exactly what we got when we reduced the system earlier. So either way you do it, you end up with the same solution. The point is that it's much faster just to multiply this vector B by A inverse than it is to augment A with the vector B and then do all of our row reductions. So if you have the inverse, you should consider yourself lucky because this makes solving systems of equations much faster. So again, at the end of the day here, there's one solution to this system, and it's given by the vector 10, 2, 4. Okay, so hopefully I've convinced you that having inverses is a useful thing. So now I'd like to attack the problem of, well, what kind of behavior do inverses exhibit, and how do I find them? So one key result in this line of reasoning is this result that says the following. Let's say that I'm dealing with a square n by n matrix. So if my matrix is square, well, it turns out that if I multiply on the right by another matrix and produce the identity matrix, that automatically tells me that multiplication on the left by that matrix also gives me the identity, and vice versa. In other words, if I know that I'm dealing with square matrices, A times B equals the identity is the same thing as saying B times A equals the identity. So that's useful. How could I use that? Well, here's a calculation. I took a matrix A and I multiplied by this matrix B to produce the 3 by 3 identity matrix. Now, if normally, if we started from the beginning of this lecture, all I could conclude here is that B is a right inverse of A. But given the context of this current theorem, the idea is that, well, once I've verified that A times B is the identity, because these are square matrices, I don't need to verify that B times A is the identity. That's actually guaranteed for me. So what does that tell me? That tells me that this B is A inverse. So this theorem is effectively cutting our work in half when it comes to verifying whether or not a matrix is an inverse of another matrix. And another important result says that the only matrices that have two-sided inverses are square matrices. So the only hope you have in having an inverse is if your matrix is square. But as we saw previously, there are some square matrices that don't have inverses. So to recap, if your matrix is square, it might have an inverse. And if it does have an inverse, you only need to check that the inverse multiplies on one side to produce the identity matrix. Okay, now what kinds of properties does inversion obey? Well, one important property is the order reversing property. If A and B are square matrices of the same size, I can multiply them together, and this produces another invertible matrix as long as A and B themselves are invertible. And if I wanted to invert that matrix, so if I wanted to apply the inverse operation to the quantity A times B, it turns out this is always the same thing as the product of the inverses of A and B together in the reverse order. So it's an order reversing property, just like transposition. Another interesting property is that inversion is an involution. If I invert a matrix twice, I always get back to my original matrix. And I have a third property. This is called a scaling rule. If I scale an invertible matrix by a number C and then I invert, that's the same thing as multiplying the original inverse by the reciprocal of the scalar I used. And there's also a transposition rule. The transposition rule says that transposes swap with the inversion operator. So the inverse of A transpose, provided it exists, is the same thing as transposing the original inverse. Okay, so now the question of, well, that's all well and good. I have these properties of inverses, but where do inverses come from? Well, let's address this issue now. So the underlying idea here is that if I want to find a matrix inverse, I'm trying to solve the matrix equation A times an unknown matrix X equals the identity matrix. And we can solve that matrix system by forming an augmented matrix by not just augmenting the matrix A we start with a vector, but with augmenting with the entire n by n identity matrix. So the first thing we do if we want to calculate a matrix inverse is we augment with the entire n by n identity matrix. The next thing we do is we row reduce that big augmented matrix. And the idea here is that we're row reducing until we reach the reduced row echelon form of A on the left in our augmentation. Now, there are two possibilities. One possibility is that the reduced row echelon form of our A is something other than the n by n identity matrix. If that's the case, then our matrix is not invertible. So we immediately have this conclusion. However, if the reduced row echelon form of our matrix is the n by n identity matrix, then this new matrix B that is emerged out of these row reductions on the right in this augmented matrix is guaranteed to be the inverse of A. So at the end of the day, it's Gauss-Jordan elimination that allows us to calculate matrix inverses. I think this is best illustrated, just like with lots of things, with an example. So here I have an example where I've taken a perfectly good 2 by 2 matrix A, and I've asked myself, well, does this matrix have an inverse? Well, it might because it's a square matrix, but in order to resolve the issue, I should augment this matrix A with the entire 2 by 2 identity matrix. Now I can start applying the Gauss-Jordan algorithm until I reach the reduced row echelon form of A on the left. I start in the upper left-hand corner where I have a -1. I make that -1 equal to 1 by scaling the first row by -1. That gives me my first pivot in the 1, 1 position, which I can clear out by taking row 2 and adding row 1 to it. Now I have a legit first pivot column, and I move right 1 and down 1 to deal with this 3. Well, this 3 will be my next pivot position, but in order to make it an actual pivot, it needs to equal 1. I can do this by scaling row 2 here by 1/3. That gives me my pivot in the 2, 2 position, but I'm not in reduced row echelon form yet because of this non-zero number above my second pivot. I resolve this issue by taking row 1 and subtracting row 2 and that zeroes out my 1, 2 position. So what has happened? Well, I've taken my original A and augmented with the 2 by 2 identity matrix, and I've row reduced, and now I've reached the reduced row echelon form of A on the left here. And importantly, the reduced row echelon form of A on the left here is the 2 by 2 identity matrix. So I've reached the 2 by 2 identity matrix on the left, and what that's telling me is that this matrix A was invertible because its reduced row echelon form is the identity matrix, and its inverse is now sitting here on the right. So we've now successfully found the inverse of A. Of course, if you were skeptical, you could verify that this is the correct inverse by taking this matrix and multiplying by A and verifying whether or not this produces the identity matrix. Here's another example. In this example, I took this 3 by 3 matrix A, augmented with the 3 by 3 identity matrix, and had a computer do my row reductions. When the computer did the row reductions, we found that the reduced row echelon form of A was the 3 by 3 identity matrix. That tells me this A is invertible, and its inverse has popped out here on the right. That's this new 3 by 3 matrix. Once again, if you were skeptical of this, you could verify that this new matrix is indeed the inverse of A by multiplying A on either the right or the left and verifying whether or not you produce the identity matrix. Here's another example. In this example, I was studying a 4 by 4 matrix A. I was curious whether or not it was invertible, so I augmented with the identity matrix and applied the Gauss-Jordan algorithm to reduced row echelon form. This time, I found that the reduced row echelon form of my 5 by 5A was definitely not equal to the 5 by 5 identity matrix. This 3 is a typo. This should be 5. In fact, the rank of A here is 3. It is not equal to 5. So this matrix A is not invertible because its reduced row echelon form is not the identity matrix. Excellent. So the Gauss-Jordan algorithm is intelligent enough to tell us whether or not a matrix is invertible and also produce matrix inverses when a matrix is invertible. Now, one thing to notice here is that what our algorithm is telling us is that the existence of the inverse of A hinges on whether or not the reduced row echelon form of A is the n by n identity matrix. So here's an example. If I took a 3 by 3 A and augmented with the identity matrix, I could find the inverse by row reducing A until I reach reduced row echelon form. In this case, I get the 3 by 3 identity matrix, so the matrix inverse of A has popped out on the right here. Well, previously we said what it means for an n by n matrix to have reduced row echelon form equal to the identity matrix. What this means is that the rank of A equals n, and that's the same thing as the adjective non-singular. So what we're finding here is that this adjective non-singular that we gestured toward when we talked about Gauss-Jordan elimination, which means that our matrix is square in full rank, is actually the same thing as saying that our matrix is invertible. And so this leads us to what's called the invertible matrix theorem. The idea is that for an n by n matrix A, there are lots of equivalent ways of saying that our matrix is invertible. One way of saying that a matrix is invertible is saying that it's non-singular. Remember, that's the same thing as saying that our n by n matrix has rank n. Of course, if our n by n matrix has rank n, that's the same thing as saying that the nullity equals 0, because the rank plus the nullity must equal the number of columns. This is also, as we've seen, the same thing as saying our matrix is invertible. When we say our matrix is invertible, that's the same thing as saying that the inverse exists. If the inverse exists, as we saw in our algorithm, that's the same thing as saying that the reduced row echelon form is equal to the identity matrix. And if the inverse exists, that means that if I'm studying the system AX equals 0, I can solve for X as A inverse times the 0 vector, and that tells me X must equal 0. We call this the trivial solution to AX equals 0. And another a way to say that our matrix is non-singular or invertible is to say that every system with A as the coefficient matrix is a consistent system. In other words, the rank of A is the same as the rank of A augmented with any vector. So these are all equivalent ways of saying that a matrix is non-singular. By the end of this course, we'll be able to add a few more statements to this list. So that concludes the lecture. Let's jump over to the Sage module and see what's there. I have two calculators posted on the website. The first calculator will do the following. So we start by inputting a matrix A. The calculator will augment that matrix with the 3x3 identity matrix, and then row reduce. This is relevant to our inverse calculation, because if the reduced row echelon form of A, as pops out on the left here, is the identity matrix, that means this new matrix on the right is the inverse of A. And if we wanted to, we could just directly calculate inverses, and the syntax for this is a.inverse, as illustrated in my code here. So if you want to just find a matrix inverse, you can use this calculator for doing that. Input your matrix on the first line here called A, and when you click evaluate, the code will print out the matrix so you can verify whether or not you made mistakes, and then also the matrix inverse. Note that the matrix I've input in both of these calculators is the same, and in both of these calculations, the matrix inverse